to have a number of superb X-ray observatories, including the Chandra X-ray Observatory, the X-ray multi-mirror mission Newton, and since about 2012, NuSTAR, and now of course we have eROSITA as well. And I'm going to talk today about results from all three of the missions shown here. And they all work together very effectively, complementing each other. Although for most of this talk, I'm going to focus on results from the Chandra X-ray Observatory, in particular on the famous Chandra Deep Field observations. And I'm going to focus today on studies of supermassive black hole growth as revealed primarily by the studies of active galaxies in the distant universe. So this work that I'll be talking about today is not just my own. I've been very fortunate over the years to work with a number of excellent graduate students. These are some of my graduate students over the years. I know Brett Lemur came and spent a couple of years with you guys there at Durham. And also I've been blessed to work with many great postdoctoral researchers, including the boss over here in the corner. Okay, and so it's been a great pleasure working with all these people, and they've all made important contributions to the work I'll be talking about today. I also am grateful to have many collaborators worldwide, including a number of good folks from the UK. Ian Smale, for example, has been a longtime collaborator on this work as well. And I also, particularly in my case, want to thank the members of the Chandra Advanced CCD Imaging Spectrometer Team, or ACES. This is an instrument that is led by Penn State and MIT and other collaborators, and it's the main instrument I'll be talking about data from today. ACES is shown here. It sits at the back of the Chandra X-ray Observatory over here and gathers the X-ray observations for about 95% of the Chandra X-ray Observatory's data. And this has been a great instrument. It's worked very successfully now for more than 20 years. And one great thing about detecting X-rays with a CCD-based detector is you're not just making images with the CCDs, but because the X-rays typically have about 1,000 times the energy as an optical light photon, they interact sufficiently strongly with the semiconductor, make enough electron hole pairs that you also, at the same time you're performing imaging, are also performing spectroscopy. And then because the CCDs are also read out very quickly, about every 3.3 seconds, you also get quite good timing information. And so for all the sources I'll be talking about today, we don't just have imaging X-ray data for them, we have X-ray spectra and timing information as well. Okay, so this is the outline for the talk today. I'd like to start off by telling you about the overall utility of X-ray surveys of active galaxies. I will then talk about the Chandra Deep Fields. I will then give highlights of some selected science results. I won't give all the technical details, just some highlights. And then I will talk about some future prospects for how the field may be advanced in the future. I'll start off by discussing the utility of X-ray surveys of active galaxies. So X-ray emission from active galactic nuclei is observed to be nearly universal, and that's extremely important from a survey's point of view. The fact that it's almost always there from active galaxies means that you can get a good census of the active galaxies out in the universe. The X-ray emission is made in the immediate vicinity of the black hole, and it's via complex processes, primarily, we believe, Compton upscattering, where you have ultraviolet and optical photons from the disk that are Compton upscattered in a very high temperature corona overlying the disk, which is kind of perhaps like the solar corona, but far more extreme, with a temperature of about 1 billion Kelvin. And that's how the X-rays are being made. Now, the details of exactly what happens down in this region are still complex and poorly understood, but we do have just empirically shown that the X-ray emission is nearly universal. When we find active galaxies at other wavelengths, they're almost always X-ray emitters as well. Now, this region close to the supermassive black hole is also highly dynamic. Here's a little movie we made to illustrate that. And we know that this region has a dynamic character, for example, from the strong X-ray variability that we observe from these systems. And that X-ray variability, in fact, is going to be important for some of the things I'll be saying later on in this talk. And so I'll refer back to that at the appropriate time. So that's one big point. The main point I'm trying to get across here again is that X-ray emission is nearly universal from active galaxies. The second big point I want to, the next, let me just finish then. One other point that I just want to show here is the typical X-ray spectral properties of these active galaxies. So we see X-ray emission from these active galaxies over a broad range of X-ray energies, extending from 0.1 keV and below all the way up to more than 100 keV. So that's like 3 orders of magnitude in energy. Now, the surveys I'll be talking about today with the Chandra X-ray Observatory and with XMM Newton span a good stretch of this spectrum. The Chandra and XMM surveys typically cover effectively between about 0.3, so around here, up to about 8 keV. Okay, and then NuSTAR, its specialized technology for imaging harder X-rays extends that effectively for deep survey observations up to about 16 keV, perhaps 20 keV in some cases. Okay, and that's a very broad bandpass. It's about 20 times the width of the whole optical bandpass. And so we have a very, very broad grasp on the electromagnetic spectrum in these X-ray observations. Now, the next big point I want to make about X-ray surveys, another reason why X-ray surveys are so effective, is that X-ray emission is highly penetrating. We all know that from the doctor's office and from the dentist's office, and that provides us with reduced absorption bias. And this is critically important because we know that the light from active galaxies is usually obscured, often substantially, by both small-scale nuclear emission in the immediate vicinity of the black hole, as well as from absorbing material on the scale of the galaxy. And X-ray emission, via its penetrating nature, can cut through and also measure these large column densities. And that's shown with this little movie I'm illustrating here. What I'm doing here is I'm essentially showing this exact same spectrum I just showed you here, but now I'm adding absorption to it with a hydrogen column density as labeled here. And you can see as you raise the column density, you get this X-ray absorption cutoff that systematically marches upward in energy. And from the location of that cutoff, you can get a good first estimate of how much absorption is present in a given system. Now, the amount of absorption that you can cut through with X-rays is quite large, particularly with the harder X-rays. To give you a bit of context there, a column density of 10 to the 23, so there, I'll show it again right there, that's about the column density through your hand. Okay, and the column density through your chest is about 10 to the 24. And so, you know, as you might expect from the doctor's office or the dentist's office, these hard X-rays can cut through lots of absorbing material. Now, moreover, another great thing about X-ray absorption is that the absorption bias drops as you go toward high redshift. Because as you go toward high redshift, of course, the whole spectrum redshifts down, and so you gain access to increasingly penetrating rest frame X-rays. And so in the surveys of the distant universe that I'll be talking about today, even though we're observing in the observed frame band up to about 8 keV or so, we're actually often sampling 20 or 30 keV X-rays, which are very penetrating indeed. Okay, and then finally, the other big advantage of these X-ray surveys is that they have low dilution by host galaxy starlight, and that can be understood just by looking at these plots here. This is an optical image and a 2 to 10 keV image of a local active galaxy. And you can see that in the X-ray band, all the starlight drops out, and you just see the black hole related light, okay, in the very central, from the supermassive black hole in the center of the galaxy. And this is critically important in the distant universe, because in the distant universe, you don't have the luxury of being able to go in and spatially resolve away all the starlight, because the galaxies are very small on the sky. And so you need a method of studying these systems that maximizes contrast between starlight and black hole related light, and the X-rays provide you with what you need there. Now, the X-rays are not perfect. Best of all, of course, is to combine the X-ray data with multi-wavelength surveys, and indeed, that's what we do, and I'll say more about that later. Okay, so those are the big advantages of X-ray surveys. Again, X-ray emission is universal from active galaxies, it's highly penetrating, and it has rather low dilution by host galaxy starlight. And those three things together have led to people realizing that X-ray surveys are great, and it's led to many X-ray surveys for supermassive black holes in the distant universe being performed. This here is a plot that shows the flux limit versus the solid angle for many X-ray surveys coming from earlier missions like Rosat and Einstein in red, with XMM Newton here in the blue data points, and then with Chandra here in the green data points. And you can see Chandra dominates the regime of very sensitive X-ray surveys down here, and I'll say more about that shortly. And of course, this ranges from sort of very narrow pencil beam surveys over here up to surveys covering the whole sky over here, such as the Rosat All Sky Survey. Okay, now my favorite surveys are the Chandra Deep Fields, and they are the ultimate in the super deep pencil beam surveys, the Chandra Deep Field North which was a 2 megasecond observation we performed with Chandra, and the Chandra Deep Field-South, which is a 7 megasecond observation that we've now performed with Chandra. And I'm going to show you images of them now. So here are the two Chandra Deep Fields. Again, this one has a 2 megasecond coverage gathered over about 2.5 years. This one has about a 7 megasecond coverage gathered over a period of about 16 years. Okay, so we can study the X-ray variability of these sources over long time scales by slicing our data set as a function of time. To give you a context of the size of these fields, where the numbers are there, but each one is about 60% the size of the full moon on the sky. So that's kind of the characteristic size that we're surveying with the Chandra, with these deep observations of Chandra. And in this one, we have about 755 point-like sources. In this one, we have somewhat more than 1,000 point-like sources. And the majority of these, here are the numbers, are active galaxies. Now remember, in these observations, we don't just have imaging data, but I can pick any one of these active galaxies, I can cut out the photons from it, and I can make an X-ray spectrum. Or I can look at how it's varied over 16 years. And that spectral and variability information is critical for characterizing these sources. Now, you may be wondering, why do the sources look so big out here in the edges of the field, and why don't there seem to be very many sources in the center? And that's just because Chandra's imaging is so much sharper in the center than it is far off axis, that the sources out here look more visually impressive, although actually there are actually far more sources down here in the center. And I'll show that now by zooming in on this little boxed region. There is that little boxed region, and these are all the X-ray sources we detect there, color-coded by their relevant X-ray energies. And to give you a sense of how sensitive these super deep X-ray surveys are, in the Chandra Deep Field-South, the faintest sources that we detect are such that we're getting about 1 photon coming in from them every 10 days. Okay, so it's 1 photon, 10 days on average, statistically, another photon, and another photon. And you know, that shows how well Chandra has been built from end to end. It is a truly fantastic observatory that you can get down to count rates of 1 count every 10 days, and it's still easy to detect such sources. Okay, now of course we cited the Chandra Deep Fields very carefully to have optimal multi-wavelength coverage. This of course is the famous Hubble Ultra Deep Field. The Hubble Ultra Deep Field sits here, this yellow region right in the center of the Chandra Deep Field-South. And there also is very extensive Hubble Space Telescope imaging over large chunks of both the Deep Field-South, shown here, as well as the Deep Field North, via, for example, the GOODS project, the CANDLES project, the 3D HST project, and so on. And in fact, I recently saw this tabulation from the people at Space Telescope. They recently tabulated how much time has been sunk just into the Chandra Deep Field-South. It's about 6 megaseconds of Hubble time has been sunk into the Chandra Deep Field-South, with all the imaging and spectroscopy and such has been done. And because Hubble actually has a rather low observing efficiency, that's about 70% of a Hubble cycle. And if you price that out over Hubble's cost, that's about $250 million of Hubble money that's been sunk into the Chandra Deep Fields, you know, to build Hubble and construct all these things. So this is a truly fantastic data set, and hopefully we'll be using it for many years to come, because clearly we have a lot to pay off given that large investment. Okay, now the X-ray data is also complemented by ultra deep multi-wavelength coverage at many other wavelengths. Keck and the VLT and other large optical spectrographs have done very extensive observing programs in these fields. There's deep ground-based imaging in the near infrared. Spitzer and Herschel have conducted some of their deepest observations in these fields. The APEX and ALMA submillimeter observatories have conducted extensive observations in these fields. Ian Smale has been heavily involved, of course, in spearheading these. And then there's also extensive superb radio data in these fields. And all of these data sets together are critically important for identifying the X-ray sources, classifying them, trying to figure out their nature, and also measuring the properties of, for example, the host galaxies where the supermassive black holes grow. And I'll tell you about some of these measurements shortly. And of course, this is another critical aspect that has kept this whole endeavor very exciting. I've been working on this for 20 years now, and I'm not bored yet. And one reason is the X-ray data have gotten better and better over the years. But equally important is the fact that the multi-wavelength data have gotten better and better over the years. And putting all that together keeps it very, very exciting. Now, here is the current status of the counterparts and redshifts. For example, in the 7 megasecond Chandra Deep Field-South, enormous efforts have been made to find counterparts for all the X-ray sources and to gather redshifts for them. And with a great deal of work in statistical source matching, we now have about 98.4% of the X-ray sources having reliable multi-wavelength counterparts. And again, just shy of 98% of those have redshifts. About 2/3 of those now are spectroscopic redshifts, which is very impressive, given that many of these sources are quite faint. 24th, 25th magnitude spectra are available for many of these things. But at still fainter magnitudes, 26th, 27th magnitude and beyond, you have to resort to photometric redshifts. But the photometric redshifts are very good. We typically have like 20 or 30 photometric bands that are used to derive the photometric redshifts. And here, for example, just shows a sampling of our estimate of the quality of the photometric redshifts for AGNs in the Deep Field-South. You can see we typically are good to a couple percent, just estimating from the photometric data, although we do have outliers at about the 6% level that we have to be careful about. These are the redshift distributions for the active galactic nuclei, which are the main focus here, as well as for normal galaxies, which I'll say more about shortly. You can see the active galactic nuclei span a broad range of redshift, from redshifts of about 1/2, where we start to have decent numbers, up to redshifts of about 4. So we're sampling a very broad stretch of cosmic time of black hole growth with these observations. And then the normal galaxies, which I'll say more about momentarily again, we get out to a redshift of about 1.5 or so. Here is the same plot, but binned much more finely, just to show you that we actually can detect spikes associated with large-scale structures in the distant universe as traced by the X-ray active galactic nuclei as well. Okay, so what are the X-ray sources that we're talking about here? What are the counterparts? Well, here's one nice plot showing them. These little cutouts, each one is 12 arc seconds by 12 arc seconds, and I plot the 68% confidence X-ray error circle on each one. Okay, and these little composites are made from B, Z, and then infrared observations. And you can see we have active galactic nuclei that are very faint, like this one, others that are very bright, like this one. And the true power of understanding these systems, of course, comes from studying large numbers of these systems, which are all characterized very well in a statistical manner, and then making statistical statements about where black holes grow in the universe, for example. Okay, so this is just one page of these cutouts. Here's another one, okay? And you can see there's lots and lots of beautiful active galactic nuclei here with very well characterized host galaxy properties, okay? Here's another page here, okay? And in total, I have about 30 pages just like this, okay? They're all published in the paper. Sometimes I just spend an hour or two just staring at these. They're so much fun just to stare at them and think about them. In any case, so those are the sources that produce, for example, the cosmic X-ray background. You're looking at them, though. Those are the galaxies where black holes grow in the universe. Okay, so just a few quick words about the detected source number counts. So in pushing the data super deep, the number counts of active galaxies, which are shown here as the blue data points, rising as you go down to fainter and fainter X-ray fluxes, reach about 24,000 sources per square degree in the Chandra Deep Field-South. That's quite impressive. This is a representative patch of sky. If you scale that up to the full sky, that's about 1 billion of these active galaxies spread across the sky. So the cosmic X-ray background is made by about 1 billion active galaxies spread all around the sky. The X-ray observations find a much higher density of active galaxies by about a factor of 20 than the deepest surveys, for example, performed in the optical band, where you try to find active galaxies with optical selection techniques. And again, the reasons for that are that the X-ray emission is universal, it's penetrating, so we can find the obscured systems that optical people have a lot of trouble finding, and we don't suffer from the severe dilution problems by host galaxy starlight. It's those same 3 factors that come back again and again and make the X-ray survey so effective. The X-ray selection also compares very well with selection at other wavelengths, particularly if you consider source purity. That is, we find almost all, not all, but almost all of the active galaxies that people find at other wavelengths. And when we say something is an active galaxy, we actually mean it. Where, for example, in the infrared, they say, well, we think this thing may be an AGN, but it's maybe only at the 60 or 70% level. We're not quite sure. Okay, when we say it, we mean it. And that's very valuable, to have a pure sample that you're highly confident about. Now, best of all, as I mentioned, is to combine the X-ray data with infrared data and other multi-wavelength data. And that's critically important. And that is, in fact, what we do to get the best complete samples of these active galaxies. We resolve about 80 to 90% of the cosmic X-ray background up to about 8 keV. And then in addition to the active galaxies in blue, we also are detecting, and I'll just point this out in passing, a large population of cosmologically distant normal and starburst galaxies, shown as these red data points here. You can see they rise rapidly toward faint X-ray fluxes, okay? And what we're detecting there is the combined populations of X-ray binaries, primarily in distant galaxies. We're so sensitive that we can detect Milky Way-like galaxies out to cosmological distances from the populations of X-ray binaries that reside in them. And I have had students that have written PhD theses investigating these as well. They're very interesting. And notably, at the very faintest soft band fluxes you can see down here, they are just starting to overtake the AGNs in number density. So all these things labeled gal here, like that and that and that, are cosmologically distant galaxies where we're detecting populations of X-ray binaries out in the distant universe. Okay, so now I want to get on to some selected science results from the Chandra Deep Fields. And here, again, I am not going to try to go and give you every technical detail of every point. You can see the papers for that. I'm just going to give you some highlights here. One thing I want to talk about for a while is this issue of what matters for cosmic supermassive black hole growth. I've assigned this topic as the PhD thesis for two very good students of mine. Guang Yang was a superb student I had, and he is now at Texas A&M as a postdoctoral researcher. And Qingling Ni is a current student with me. She's also fantastic. And what do I mean by this question? Well, what we're trying to answer in this work is what properties of a galaxy set how its black hole will grow. Is it the stellar mass of a galaxy that primarily sets how black holes grow? Is it the star formation rate of a galaxy? Is it galaxy structure? For example, compactness, which is a measure of the mass to size ratio of a galaxy, or is it the environment? Is it the environment in which a galaxy lives that sets how its black holes grow? Well, we've performed extensive work investigating all of these issues. It published in about 7 or 8 papers now. I can't cover all those papers, so I'm going to focus just on a couple of recent results that we're excited about. One of them, of course, is motivated by these famous relations between black hole masses and the bulge properties of galaxies, which have now been established for more than 2 decades and seem to be very clear that a black hole knows quite a bit about the galaxy bulge in which it's living, despite the fact that the black hole compared to the size of the bulge is like that of a pebble compared to the Earth. So a big question is, how do you get these relations? Are these just the result of some kind of statistical averaging process that galaxies undergo? Or is there a true connection between black hole growth and galaxy growth? That's the type of issue we're trying to address in this work. Notably, despite the fact there are these clear black hole bulge connections, the connections are not nearly as clear when you look, for example, at black hole masses compared to the total masses of galaxies. That's what's shown here. There is still a broad relation there, but it's much less clear, much less tight than the bulges. So there really seems to be something special about the bulges. That's also true if you look at black hole mass compared to the disk masses of galaxies. Not much of a correlation there either. So again, there's something special about the bulges. So that motivates the work that I'm going to be talking about now. This motivates the importance of morphology. So clearly something is special about bulges, and so we want to investigate, can we see connections between bulge growth and black hole growth in the distant universe? And to do that, well, you're going to have to use morphology. So we've used a large sample of about 10,302 galaxies in the 5 famous candles fields. These include the 2 Chandra Deep Fields as arguably the 2 best of them, but then has 3 other fields, EGS, UDS, and the Cosmos field. So we combine all those data together. These fields have, via the CANDLES project, superb, extremely deep, extremely high resolution morphological measurements out of the H band. So you're measuring rest frame optical light even out in the distant universe. And the morphologies have been measured with machine learning approaches by Huertas Company et al. And we use their measurements as well as our own independent measurements to test them to separate galaxies out by their morphologies. We separate them into bulge-dominated systems, which are these red-framed panels up here at the top, okay? And then non-bulge-dominated systems as the blue-frame panels down there. And you can see these are clearly bulge-dominated systems. These clearly have other stellar components that are present morphologically. And why are we doing this? Well, again, the key idea is to try to remove the non-bulge components, because they don't seem to correlate very well with black hole growth. And we're trying to get systems where we can measure their star formation rates. And for a bulge-dominated system, the bulge star formation rate will approximate the total star formation rate of the galaxy. Because again, supermassive black hole growth, we have reason to believe, is maybe related only to the star formation rate of the bulge. So essentially what we're trying to do is we're trying to measure the time derivative of this diagram. Okay, this diagram is stellar mass versus bulge mass or bulge luminosity. And effectively what we're trying to measure is that the time derivative of this, which would be the black hole accretion rate, and the time derivative of this, which would be the galaxy's star formation rate. That's what we're trying to get at. And so we've done that with a superb sample. There's many technical details I won't go into, but one thing I do want to talk about is how we treat the X-ray data. And this goes to an important line of thinking that I believe was led initially by Ryan Hickox, who again worked with you guys there in Durham, and Dave Alexander was heavily involved. And it goes to the question, which I often ask myself when I look at data like these, and that is, what would these observations look like if I were not to have performed the Chandra Deep Field experiment right now, but I were to have done it in 1 million years, or 10 million years, or 100 million years? Would it be the same pattern of spots on the sky? Would this one still be there and that one still be there at the same place? Or rather, because we know active galaxies very strongly just on human timescales, let alone on timescales of millions of years, would it be a different pattern of spots on the sky? And should these data be interpreted rather as a kind of statistical sampling of the types of galaxies that like to grow their supermassive black holes? And there's good reason to believe this is the correct interpretation, that you can't imagine that the exact pattern of spots we see on the sky in the X-rays would be the same in 1 million years, but rather this is a statistical sampling experiment, and we can use it in that sense. And so then what we do is we take black hole growth to be ergodic, and so you can average over samples of active galaxies to learn something about their long-term time averages, to try to measure the long-term average black hole growth of these systems. And that is in fact how we do things. So we take samples of galaxies with predefined properties of some type, star formation rate or stellar mass or something like that. And we then average over the measurements via using the direct detections as well as the non-detections, which we probe via stacking. I'll say more about that in a little bit. And we then measure black hole growth on average. And here's what we find when we do that for this particular experiment. Here is our attempt to make the time derivative of this diagram, okay? Here it is. Here is the black hole accretion rate versus the star formation rate. So we've taken samples of galaxies with known star formation rate, and we then measure their average black hole growth from the X-ray data. And we find at redshifts of 0.5 to 1.5 and 1.5 to 3, fairly good correlations between the black hole's growth rate and the star formation rate, between, again, how much the black hole is growing and how much the bulge is growing. And that seems to be present over a broad stretch of cosmic time. When, for comparison, we look at the non-bulge dominated systems, the ones that have all these other morphological components present, the correlations are not nearly as clear. You can see that there. You might still expect there to be some relation there because these systems do still have bulges, but it's a lot less clear. And so it really seems to be the case that if you home in on just the bulge component, you can actually see pretty clear connections between black hole accretion rate and star formation rate. And the fact that these exist over a broad stretch of cosmic time suggests to us that this diagram is not just an accident of galaxy averaging of some kind, but rather is a true relation, because we can see the apparent lockstep growth of black holes and galaxy bulges out into the distant universe. Okay, now we've tested this quantitatively with partial correlation analyses. Natural things you have to wonder when you look at a plot like this is this a truly fundamental correlation, or is this rather just a secondary correlation driven by some other correlation that is more fundamental? And we test that with partial correlation analyses. For example, we have the star formation rate fight it out with other things like stellar mass. And we find that for the bulge-dominated systems, indeed, the star formation rate seems to be the fundamental correlate, whereas stellar mass is a secondary correlate and perhaps is entirely being driven by the fundamental relation, okay, of star formation rate. So these really do seem to be fundamental relations rather than secondarily induced correlations. Now then, if we take the best fit from these measurements, which is actually statistically consistent, both at redshifts of 0.5 to 1.5 and 1.5 to 3, this is the fit that we get. The black hole accretion rate, time averaged, is equal to the star formation rate in log minus 2.4 rate. So in other words, the black hole accretion rate divided by the star formation rate for the bulge-dominated systems is about 1 part to 302, which is similar to the ratio of black hole masses and bulge masses in the local universe, which is very pleasing. You know, things seem to add up correctly. You take the growth that we see and you produce the same ratio of masses that we observe in the local universe quantitatively. We take this, as I just said, to be evidence of coevolution instead of a kind of merger-based averaging, because we directly are observing lockstep growth of black holes and bulges over a broad stretch of cosmic time. And we hope to improve this work in the future by going and measuring bulge star formation rates in more galaxies, for example, with the James Webb Space Telescope, and also by constraining gas supplies in these systems with ALMA. And some work with ALMA is in fact going on presently. Now, I've just highlighted one important result from this broad body of work. I would just mention one other thing. Now, the results that I've just described, this nice relation between black hole accretion rate and star formation rate, is we think I tried to be quite compelling, but it is probably only the first approximation to a more complex truth. And Qingling Ni has recently done a substantial amount of work, for example, looking at other morphological correlates of black hole growth. In particular, she has found that black hole accretion rate also shows clear connections to galaxy compactness, which essentially is a measure of the mass to size ratio of galaxies. Here's one way it's commonly measured. You measure the stellar mass within a kiloparsec of a galaxy, and essentially you're measuring the mass density over the central kiloparsec. And what you find is that the black hole accretion rate correlates significantly with galaxy compactness as well. Again, across a broad range of cosmic times, as shown here, there's very clear correlations there, okay? And these are not just secondarily induced correlations. Partial correlation analyses, again, show that. And so one way to interpret this is that there may be a common origin of gas fueling of supermassive black holes. There may be a common origin of the gas that fuels the supermassive black hole and drives the black hole growth, and the gas that is present in the central kiloparsec of a galaxy. That's what we think may be driving these. And these relations are interesting for a variety of other reasons. For example, in the local universe, people have found these so-called supermassive black hole monsters, which are galaxies where the supermassive black hole is much more massive than you would expect from the black hole mass bulge mass relation. And these are often actually found in relatively compact galaxies. And these compactness relations with black hole growth may have a significant part in explaining why the black hole monsters exist. Okay, so that's one thing I wanted to talk about. The next thing I'd like to say a few words about is supermassive black hole growth in the first galaxies. And Fabio Vito, who has been a postdoc with me in recent years, has done a substantial amount of work on this, and we continue to collaborate on these efforts presently. One thing that we've done, with again using the Chandra Deep Fields, is we have measured as best we can the space density and the obscured fraction of active galaxies at redshifts of 3 to 5. And we do this not for just the luminous quasars, which are well probed by surveys like Sloan and things like that, but rather we do it for the sort of typical moderate luminosity active galaxies where you need the ultra deep X-ray surveys to perform the work. And here are some of our measurements. This panel essentially shows the decline with redshift in the number density of active galaxies for luminous active galaxies in blue, and then moderate luminosity active galaxies in green, and then lower luminosity active galaxies in red. And the best data points are these open ones here, which are incompleteness corrected. And what we find is that surprisingly, if anything, at low to moderate luminosities, again, the red and the green data points, the decline with redshift is actually slightly steeper than at high luminosities, which is surprising. You might have thought that the more massive things, would take a while to fire up, at least in the very distant universe, but rather we see the opposite. We find that if anything, the more massive things become relatively more numerous relative to the low luminosity things as you go to higher and higher redshifts. And this has important implications, for example, for the Athena mission, which has as one of its primary goals to find these moderate luminosity active galaxies. Unfortunately, our work is suggesting they may be fairly rare and challenging for the Athena folks. We also have measured the obscured fraction of active galaxies out at high redshift. And as at low redshifts, we find a very large fraction of obscured systems And this is for quite high levels of obscuration, 10 to the 23. We find something like 60% of the systems remain highly obscured out in the distant universe. And that means that X-ray surveys will remain essential for studying these systems in the distant universe because they're going to be very hard to find with other approaches. Okay, now we'd like to push to even higher redshifts. Most of what I've been talking about so far sort of probes this part of the black hole mass versus time after the Big Bang diagram. These are the very powerful quasars that surveys like Sloan have found. We can probe systems over here, lower mass black holes at similar redshifts. But what one would like to do, going still further, would be to push to even higher redshifts and to start setting constraints on how the first black holes grew at even earlier cosmic times. And there's lots of interesting possibilities here. They may have grown via a kind of Eddington limited growth for a while, or perhaps they stalled for a while and then grew via hyper-Eddington growth, or alternatively, you may have had direct collapse of gas clouds in the early universe so that these systems kind of got a jump start at 10 to the 5 solar masses. And we're trying to constrain these types of ideas as well. Now, we can't do this even with the Chandra Deep Fields. This is beyond the sensitivity that we currently have for the Chandra Deep Fields, at least for direct detection. So we use a bit of a trick to get there. And the trick that we use is stacking. And this is a plot that illustrates the stacking technique that we are utilizing. This is a plot that was made by my student, Brett Lemur, who again was with you guys for a number of years. And I call it the romantic example of stacking because Brett made this plot around the time he got engaged to his girlfriend. And so I find that to be a quite nice name for it. And so what Brett did here is quite interesting. He took 30 T candles and he put them on his stairs. And he took an observation, an exposure with his camera of them, a 3/100-second exposure. And here is a typical T candle with a 3/100-second exposure. He took another exposure with a 1/1000-second exposure, and here's a typical 1/1000-second exposure, which has obviously a lot less information in it than this one. But the idea of this stacking, if it holds up, is that if you stack all 30 of these T candles up, you should be able to recover something from a bunch of images like this that looks like that. And here is the stack. Okay, here is the stack. 30 candles, each with 1/1000-second exposure, gives you a 3/100-second effective exposure. And in the image, you can see the flame very nicely. You can see the candles wax. You can even see some evidence for the wick there. And so the approach seems to work. And we use this exact same approach to probe galaxies and their black holes in the distant universe. And here's what we do. Fabio has done a lot of work on this. We compile the best available samples of high redshift galaxies at the Chandra Deep Fields. And we then stack them up, again, aiming to push as faint as possible to constrain supermassive black hole seeds in the distant universe. And we perform X-ray stacking of individually undetected galaxies. And in different bins of redshift and different bins of stellar mass, we have different numbers of galaxies. For example, in this particular bin, the lowest redshift bin that we probe, where we consider galaxies of all available masses, we have about 1,400 objects that we stack, each one of which has about a 7 megasecond exposure. So if you stack 1,400 galaxies with a 7 megasecond exposure each, you get an 8.2 gigasecond effective Chandra observation. So this is this is a 265-year Chandra observation, okay? And you can detect those galaxies. And this is quite remarkable. The Chandra would operate well even if you expose for 265 years. So in other words, if you took Chandra and you pointed it at the Chandra Deep Field-South for 265 years, something that I would love to do, but I doubt my proposal would be accepted, you would detect those galaxies, okay? And this is true also at redshifts of 4.5 to 5.5, and at still higher redshifts, 5.5 to 6.5, we don't get direct detections, but we get a very valuable upper limit. And we find that the signal that we detect here is in fact primarily present coming from the most massive half of the galaxies. Most of the flux here is also present if we only stack the most massive half of the galaxies there and there. So then the question becomes, what is the nature of the signal we're detecting here? And we've done a lot of work investigating that based upon our understanding of the X-ray emission from galaxies. And our best estimate is the signal that we detect here is in fact not primarily from supermassive black holes, but is primarily from high mass X-ray binaries in these distant massive galaxies. So in other words, even though we're detecting signals from these things, we're not detecting much black hole growth from them, which places very tight constraints on the amount of seed growth that is possible in these systems. And this here kind of shows our combined constraints from direct X-ray detections, shown as the black data points, the solid black data points, as well as our stacking limits shown here. And what we essentially find is that most black hole growth at high redshift has to be occurring in the short directly detectable AGN phase. It's very difficult, nearly impossible, to hide any significant additional black hole growth from a kind of continuous low rate accretion mode that's spread across all the other available galaxies. There just is no room for it. And so this is a very tight constraint because there's no place to hide any more black hole accretion. We've investigated all the galaxies that are there. And notably, our constraints lie considerably below many of the theoretical models that have been put forward in recent years. And many of these models have now been revised, such as this one by Marta Volunteri, to agree with our data better. And so we're providing very valuable constraints here on how the first black holes are growing. Okay, and we hope to push this to higher redshifts in the future. We already have performed stacking of Lyman break galaxies at still higher redshifts. We take the redshift 6 and 7 and 8 Lyman break galaxies that have been found in the Deep Field-South. We stack them. We don't detect them right now, but again, we get very useful X-ray upper limits. And we are looking forward to pushing this line of work further with the launch of the James Webb Space Telescope, which will provide us with large samples of high redshift galaxies with better redshift identifications, and it will allow us to remove interlopers that we think are at high redshift, but actually are not. That will clean up the whole procedure from end to end. And so we aim to push these types of stacking analyses to redshifts of 10 to 15 soon with the samples from JWST, and that will let us to truly start to constrain the first black hole seeds. Okay. Now I see I'm running short on time, so I'm not going to say much about the faint fast X-ray transients, which is another fascinating endeavor. I will just say briefly that we have detected serendipitously faint fast X-ray transients, 2 of them in the Chandra Deep Field-South. We didn't try to detect these, they just popped up in our data. These have kind of a fast rise in power law decay. We think one of these may be an orphan off-axis gamma ray burst afterglow. And this one here turns out to be particularly exciting. We published it in Nature. We think this one may in fact be a merger of 2 neutron stars that led to the formation of a millisecond magnetar. And you could read about our thinking on it in this paper if you're interested. We also have performed a systematic search for these faint fast X-ray transients and quantified how common they are out in the universe. And this has a lot of potential for the future. Missions like Athena and the Chinese Einstein probe should detect more than 1,000 of these faint fast X-ray transients due to their large grasps. And so this is something Athena people should be thinking about for the future, because there's an additional great science that's going to serendipitously fall out of missions like Athena that right now the data policies are actually not very well designed to accommodate. Okay, so I'm going to end by saying a few words about future prospects for X-ray surveys of active galactic nuclei. First of all, I want to stress that Chandra and XMM-Newton are wonderful missions. They've been going for more than 20 years now, and they're still going great. This plot basically shows the status of all the Chandra subsystems. The details don't really matter exactly. The point is that Chandra is doing great, and that both Chandra as well as XMM-Newton can likely last until 2025 and beyond. So we're very fortunate. We can hope for many more years of exciting X-ray surveys. Now, I personally think that it's time now to take on some really aggressive projects with these observatories, not to just do more of the same of what we've been doing for the past 20 years, keep doing that at some level, of course, but to start doing some really aggressive things. So here's an example of a really aggressive thing that I've been working on. This is the XMM-SERVS survey. And the idea here is to obtain high quality X-ray coverage of the LSST Deep Drilling Fields. So I've been heavily involved in LSST since about 2005, the Rubin Observatory. And the Rubin Observatory was forecast prior to COVID-19 to begin full science operations in 2023, and now may be delayed by about a year or so. But when it ultimately is up and going, it will be very exciting. It will conduct an extremely high quality time domain sky survey over about 18,000 square degrees of the southern sky. But in addition to its main survey, it has also chosen already 4 deep drilling fields that it is going to observe considerably more intensively. And the fields are labeled here: Cosmos, XMM-LSS, the Chandra Deep Field-South, and the Elias S1 field. Each of these will have a 10 square degree coverage. The black circle here in each case shows the LSST field of view. And these fields have superb multi-wavelength data. You can see that by all these colored regions here, which show coverage in the infrared and with for example, the Veil survey that Amanda Banerjee is running, and with many other surveys that are currently being executed or have been executed in recent years. There is, Mark Lacey, for example, has led excellent Spitzer coverage. The grayscale in each case shows the high quality Spitzer coverage in each of these regions. And these ones already have full Spitzer coverage over essentially the entire planned LSST deep drilling field. And LSST is going to observe these things every 2 to 3 nights for about 10 years, 900 epochs or so in total. Be a phenomenal data set for studying active galaxies. And we have been trying to get X-ray coverage to complement all the multi-wavelength data, because right now there has been in recent years rather little high quality, several square degree X-ray data to complement all these multi-wavelength data and to prepare for LSST. Cosmos had it, but the other fields, well, and XMM-LSS had some, but the other fields really didn't have it. And so we've been building that up. And we essentially can't cover the full deep drilling field, so we're covering the prime regions, the regions making up part of the so-called Spitzer extragalactic representative volume survey. It's these blue regions here are the regions that we've been covering with XMM Newton. And here is our plan. We are getting coverage of XMM-LSS. We already have completed XMM-LSS, the Chandra Deep Field-South, which is now largely done, and LSS-1, which is now largely done. We're surveying them all the 50 kilosecond depths. We expect to detect among these 3 fields about 11,000 AGNs, many X-ray groups and clusters. These will allow a lot of exciting immediate science and also have great legacy value, again, as LSST and dark energy survey deep drilling fields, as massive spectroscopy fields for moons and PFS, as intensive submillimeter fields with Toltec and ALMA, and furthermore, as multi-object spectrometer reverberation mapping fields. All that's going to be going on in these same fields that we're getting the X-ray data for. And the X-ray data will serve as a kind of ground truth active galaxy sample for calibrating AGN selection. And we hope then to take what we learn from the LSST properties of the X-ray sources and use them to select active galaxies over the full 18,000 square degrees of LSST. And we should find many tens of millions of active galaxies that way. We already, as I mentioned, have results from the XMM-LSS field. There we've detected 5,242 X-ray sources shown here. They have 90% of them we already have good identification rates for, and more than 70% of them have spectroscopic or high quality photometric redshifts as shown there. So that's already done and delivered in this nice paper by Qingting Chen, who was a postdoctoral researcher in my group and did a huge amount of work for this. Then for the Chandra Deep Field-South, the data have been coming in recent months, well, over the past couple of years, but have just been finalized in the recent months largely. The work is being led by Qingling Ni, shown here. This is the original Chandra Deep Field-South. This is the so-called extended Chandra Deep Field-South. We now have this beautiful panoramic X-ray coverage, okay, over about 4.6 square degrees. We have about 3,990 X-ray sources detected. Almost all of them are new. We have about 92% of them already having reliable multi-wavelength counterparts. We have used hypersuprime cam imaging as well as voice imaging and video and SERVS data to compute high quality photometric redshifts and spectral energy distributions for these systems. And in addition to the Deep Field-South, we also have about 2,400 more X-ray sources in LSS-1 that we're currently characterizing. And you can see this website if you're interested in details. We're going to release these publicly as soon as we can get it all done. And then we'll start pressing out all the science, which will last probably for decades, investigating all the X-ray sources in these fields. So we're very excited about this for the future. And again, complementary multi-wavelength data is now flooding in from XMM-SERVS, including with Meerkat. The MIGHTY survey is getting excellent radio data. Toltec has selected several of these fields for deep submillimeter mapping. That will enable further ALMA observations. And then there are many spectroscopic surveys, DEVILS, MOONS, PFS, Foremost Waves, and the Sloan Digital Sky Survey 5, which will be doing time domain reverberation mapping that will, again, complement all the X-ray data and allow very exciting science for the future. Okay, and I have to end very briefly as an X-ray astronomer by talking about new and future X-ray missions. I'll keep this very brief. Clearly, eROSITA is extremely exciting. It's now gathering lots of wonderful data. It will ultimately generate a survey that's about 20 times more sensitive than ROSAT, filling in this part of the survey's diagram very effectively. We also need more Chandra Deep Fields. Right now, we only have 2. I would obviously like to have 100 Chandra Deep Fields, but I think if I wrote a proposal for 100, it would not be approved. And so we need facilities that enable this. And a mission like Athena should be able to do that. Athena will not be able to reach quite the depths of the 7 megasecond Chandra Deep Field-South, but it will get close, and it can cover much more solid angle with extremely sensitive Chandra Deep Field-like observations. And that will be very exciting for the future. And there's other missions, such as the proposed STAR-X mission, that will be able to do this as well, and perhaps even sooner. And then finally, some of us are dreaming about even more aggressive missions that would go beyond what Chandra can do. There's a mission called LYNX that's currently being studied here in the US, which is a NASA flagship study that would give you a Chandra-like angular resolution with about 30 to 50 times Chandra's effective area and a larger field of view. And with this mission, you could hope to get about 40 times the sensitivity of Chandra. Here are the deep fields. You could go well beyond the Chandra Deep Fields, way down to here. And what this mission would allow you to do is conduct extremely sensitive surveys. And here's an example. Here is the actual 7 megasecond Chandra Deep Field-South data. Here is a simulation that Ryan Hickox made of a 1 megasecond observation with LYNX. And you can see, you obviously detect all the Chandra Deep Field-South sources very well, and you detect tons of other sources as well. Many of these will just be distant galaxies. You're seeing the X-ray binary populations of distant galaxies, but among some of these, we hope will be the redshift 10 seeds of the first supermassive black holes. We aim to detect something like 30,000 solar mass black holes, including obscured systems. And with these types of observations, you could discriminate between whether the first black holes grew from the low mass population 3 remnants of stars, or whether they grew from direct collapsed black holes by measuring the luminosity function and the hosts that you detect. And so with that, I will end. And thank you very much for your time. And I'm happy to take any questions.
Thanks a lot, Neil, for a great talk. So we'll